Hi, I'm Jung Lee. Um, our project is to build an efficient automatic irrigation system. Uh, to, be, to begin with, I'd like to start by looking for problems. First is water waste. Water is very important for plants to grow, but if you give a plant too much water, the water will evaporate or seep under the ground. It is financial loss. Second is low power. The cost of running a system should be low, saving more money. And with low power, the system has the possibility of running on the solar power. Our main crop is corn. Why did we choose the corn? Because the corn is widely cultivated in the world and the most produced in the world. Like this, the corn is the first one. As you can see, the corn is the dominant crop in the Midwestern U.S. It has even been called the corn belt. So we thought our study will have the greatest impact on corn. So how to solve this problem? So we try to solve it using LoRa and MAP. LoRa is low power wide area network. Let's check LoRa's characteristic. Its data rate is slower than 4G or 5G, but communication distance and energy efficiency is better than them. So we thought it is best things our system. Next is MAP. MAP definition is management of low depletion. It means low soil moisture a plant can withstand without water stress. This point is 0% of depletion point. Over time, the soil dries out. Depletion points getting higher when depletion point reaches max. The irrigation system begin adding water. To irrigate, we needed to how much water the soil can hold. So we use the AWC. AWC is available water holding capacity. And AWC depends on soil type. So for example, this part is sandy loam. Sandy loam AWC, I'm sorry. This part, sandy loam average AWC stands for 0.11 values in water inches per soil inches. So this part depth is 6 inches. So sandy loam AWC is 0.66 inches. So this part is silty clay loam. Silty clay loam average AWC is 0.18 and depth is 18 inches. So silty clay loam AWC is 3.24 inches. So total AWC is 3.9 inches. Using that, we can get how much you have to water. Let's calculate. First, we can find the met point in this table. This table shows the recommended met point for each crop of each stage of its life. The corn is 40% to 50%. total AWC times MAP. And if you have a lower efficient sprinkler, you should be more water, so gross application will be higher. Then we have already got the GA, and A stands for area in square feet, Q stands for flow rate per plant in gallons per hour. So we use this formula, we can get how much we have to irrigate. Okay, now I explain our system. We made the automatic irrigation system. This is making an irrigation system, and this part is sensing the field sensor data, and it's automatic irrigation system. So let's see how to gather the data. First, the end node check the field's temperature and humidity and soil moisture. Then the end node and or gateway is connected by using LoRa. The radio head libraries make the connection wireless. So sensor data is sent every 20 seconds. And then inside of gateway, the bridge libraries pass the sensor data to links part from the microcontroller. And then finally, process libraries to send sensor data to ThinkSpeak website. The website shows data using that graph, and you can get data using REST API. Then, how about irrigation control? First, server observes the data. When the data matches the irrigation conditions, the server send the packet to the gateway. Then, when basic libraries receive the packet, the gateway pass the packet to the end node. Finally, end node begin irrigation. The server determines when and how much to irrigate by considering math and soil moisture and period. So to sum up what we did until now, first we researched how to effectively water and reduce water waste, and gather sensor data using by LoRa, and control the irrigation. Then what we are going to do, first, research the relation between soil moisture and mud. Second, consider its stage of constant life cycle and weather API. Last, we try to test in a small farm. Thanks for your attention.